You're tuning in today because you understand that in something as complex as an aircraft, even the seemingly basic components are absolutely critical.
Definitely.
You sent us some really detailed material excerpts from a chapter focused entirely on aircraft fluid lines and fittings.
Yeah, it's pretty thorough stuff.
Now, while they might look like just tubes and connectors, these parts are, well, they're the lifeblood of so many vital systems, hydraulics for landing gear, fuel lines.
Exactly. And what's fascinating about the material you've provided is how deeply it goes into the nuances. We're not just talking about pipes here. We're exploring the world of rigid metal tubing and flexible hoses.
The two main types.
Right. The two fundamental types that make these aircraft systems work.
Okay, so our mission today, drawn straight from your sources, is to really understand the essentials of these fluid lines and fittings.
Get to grips with them.
Yeah. We need to cover the materials, the different kinds, how they're put together, installed, identified, and inspected, of course.
All the key aspects. And I think there's some surprising details in there.
I've got a feeling we're going to uncover some surprisingly intricate details. Let's jump in.
Absolutely. Let's dive straight into those rigid fluid lines. It's quite telling to see how the materials have evolved. The chapter mentions the early days of using copper tubing.
Copper, like an old plumbing, seems a bit, well, heavy for a plane.
Precisely. It was workable, but yeah, modern aircraft predominantly rely on aluminum alloy, corrosion-resistant steel, and for the cutting-edge stuff, titanium.
Right.
The source material even breaks down why specific aluminum alloys are chosen. For instance, alloys like 1100H14 and 3003H14. They're used in low-pressure environments.
Like instrument lines, maybe? Ventilation?
Exactly that, where weight and ease of shaping are key, low-stress areas.
So what happens when the pressure ramps up?
When we move to low to medium pressure systems, think hydraulic and pneumatic systems up to maybe 1500 psi fuel, oil lines, you'll find alloys like 2024 T3, 5L520, and 61061 T6.
Okay, stronger stuff.
A stronger balance of strength relative to their weight. So you see the trend. Lower stress, lighter alloys, higher demands, stronger materials.
That makes perfect sense. Now, steel, that sounds like it's reserved for when things get really demanding.
Exactly. Corrosion-resistant steel, or CRES. You'll see grades like 304, 321, 304, 18 hard. That's the go-to for high-pressure hydraulic systems. We're talking 3,000 psi and above.
So landing gear, flap.
Yep, landing gear, flaps, brakes, and it's absolutely essential in fire zones.
Oh, okay.
And what's interesting is the tubing walls might be thinner than aluminum for similar jobs, but steel's inherent strength means the weight penalty isn't huge, and you get that crucial strength boost.
That strength-to-weight equation, again, always key in aviation.
Always.
The material also points out using steel where there's a higher risk of FOD, foreign object damage.
Right, around the landing gear, places where debris gets kicked up. Makes sense.
And the fittings for steel, usually swedged or MS flareless.
Correct. And identification is stressed. Steel tubing usually has markings, manufacturer, SAE number, material condition.
Now let's move on to titanium. It's presented as the premium choice.
It is, pretty much. Titanium 3AL 2.5V is used in high-performance aircraft hydraulic systems, typically above 1,500 psi.
Because it's even stronger and lighter than steel.
Exactly. Incredible strength-to-weight ratio. You'll often see cryofit or swaged fittings used with it.
Okay. But there's a big warning about titanium, isn't there? Something about oxygen.
Absolutely critical. Cannot stress this enough. Titanium and its alloys are highly reactive with oxygen.
Reactive how?
If a fresh titanium surface hits gaseous oxygen, even at low pressures, it can spontaneously combust.
Wow. Okay. So keep titanium far away from oxygen systems.
Completely separate. Always. That's one of those details that really highlights the level of care needed. It's a fundamental compatibility issue.
Which brings us back to identification. Getting the material right is vital, especially for repairs. Visual checks aren't always enough, the source says.
That's a key point. You might tell aluminum from steel generally, but telling specific alloys apart, visually, very tough.
So you rely on the markings?
Absolutely. Meticulously compare markings on the replacement tube with the original. For aluminum, larger tubes often have stamped markings.
And smaller ones use color codes.
Yes, color-coded bands. Figure 9:1 in the material shows that. White for 1100 alloy, green for 3003, red for 2024. Sometimes single bands, sometimes two colors.
Good visual guide.
And if the markings are gone, hardness testing is mentioned as a reliable backup.
Okay, so once you've ID'd the material, how do you work with it? Sizing and fabrication.
Right. Metal tubing is sized by its outside diameter, OD. in 16ths of an inch.
So number 6 tubing is?
616ths, or 38-inch OD. Number 8 is 816ths, half an inch OD. Simple enough.
Then the wall thickness.
Also usually printed on the tube, in thousandths of an inch. If you need the inside diameter, just subtract twice the wall thickness from the OD.
Got it. Now, ideally you replace a damaged line, but sometimes you have to fabricate one, right? Maybe reuse the old fittings.
Exactly. If a replacement isn't available, fabrication is necessary. And yeah, salvaging good fittings is common.
So what are the core fabrication processes?
4 main ones: cutting, bending, flaring, and beading.
Okay.
For really small soft tubing, maybe some minor hand bending during install. But for anything 14-inch OD or bigger, you need proper tools.
Let's start with cutting. A square, clean cut is vital, it seems.
Absolutely. No burrs. For softer metals like aluminum, copper, a standard tube cutter works well. Figure 9-2 shows the technique: rotate, gradually tighten the wheel.
And for harder stuff, steel, titanium.
The chapter mentions specialized chipless cutters, or even a fine-tooth hacksaw like 32 teeth per inch to get a clean cut.
And getting rid of burrs afterwards is non-negotiable, inside and out.
Critically important. They mention knives, the cutter's deburring edge, or special tools like in Figure 9-3. But the big warning is, don't reduce the wall thickness doing it.
Because that creates a weak spot.
Precisely. Could lead to cracked flares, failures under pressure. Oh, and a useful tip they mention: clamp small tubing in a flaring tool held in a vise for easier cutting.
Clever. Okay, on to bending. Goal is smooth curves, no flattening, no kinks.
Right. Maintain that circular cross-section as much as possible. For larger tubes, hand benders are standard. Figure 9-6 shows some.
And the tool tells you what size tube it's for.
Usually stamped right on it, yeah. Like in Figure 9-7, you line up marks on the bender with marks on the tube to get the angle right. Figure 9-5 illustrates that.
Is there a limit to how much flattening is okay?
There is. The smallest diameter in the bend shouldn't be less than 75% of the original OD.
Okay.
Figure 98 shows good versus bad, bends, flattened, wrinkled, kinked. Those are definite no-goes.
And for big production runs or really hard tubes?
They mention CNC benders, like in Figure 9-9. And there are standard bend radii you need to stick to, listed in Figure 9-4. Helps maintain strength and flow.
What about filling the tube with sand or fusible alloy for bending? Seems different.
It's an alternative method, yeah. Used when standard benders aren't quite right for the job or the tube type.
So you fill it, plug it, bend it around a form.
Basically. Fill with fine, dry sand or a low-melt alloy. Bend it. Then, crucially, get all the filler out afterwards.
How do you get the alloy out?
Carefully heat the tube, usually in hot water, never direct heat. You can make the alloy stick, let it melt out, handle it safely. Make sure it's completely clean inside.
Right. Moving on to flaring. Making that bell shape on the end for flared fittings. Single and double flares mentioned, Figure 9-10.
Correct. And these flares have to be perfect, especially under high pressure. Geometry, finish, everything.
Because a bad flare leaks.
Or fails completely. Too small, too big, crooked, all bad. And the key takeaway: you cannot fix a bad flare by just cranking down the fitting nut.
You'll just damage it more.
Exactly. Makes it worse.
And the flare angle is super specific. 35 to 37 degrees for aircraft, never the 45-degree automotive type.
Absolutely not. Figure 9-11 shows why they're incompatible. Standard hand flaring tools, like in Figure 9-12, have a block, a yoke, and a pin.
Impact type or rolling type pins?
Both exist. Rolling type is often preferred for softer metals, aluminum, copper, brass, not steel or titanium. Clamp the tube, make sure it sticks out just a bit. Use the yoke to press the pin in. That forms the flare.
Now, for smaller, softer aluminum tubing, 38-inch OD or less, the material says a double flare is required. Why double?
It gives a much stronger, smoother, more concentric sealing surface.
Yeah.
Better resistance to pressure and the shearing forces when you tighten the fitting. Just more robust.
How is it done?
The two-step process. Use a special adapter in the flaring tool first to kind of bell out the end. Then you fold that bell back on itself to create the double thickness. Figure 9-13 shows the steps.
And sometimes you need to anneal the tube end first.
For some alloys, yeah. Soften it up a bit to prevent cracking during the double flaring.
Okay. Last fabrication step. Beading. That's for attaching hoses with clamps, right?
Yeah.
Low, medium pressure.
Exactly. Creates a raised lip or bead for the clamp to grip over the hose.
How's that done?
Hand tools, machine rolls, grip dies. The chapter focuses on the hand tool, Figure 9-15, good for tubes from about 14-inch up to 1-inch OD.
Process.
Lubricate the tube end, use the right size rollers in the tool, rotate it around the tube, gradually forming the bead. Pretty straightforward.
Okay, tubing is cut, bent, flared, or beaded. Now, fittings. Used to connect tubes to things, other tubes, hoses. Some need flares, some don't.
And beading is for hose clamps. Let's start with flareless fittings. They skip the flaring step, which sounds convenient.
But they need something called presetting.
Right. It's a specific setup process. Figure 914 shows it. Cut the tube square, deburr it, lubricate the outside. Then you tighten the nut until an internal sleeve bites into the tube.
And then tighten it more.
A specific amount more, based on the tube material and size. Then you inspect carefully. Check tube extensions, sleeve contact, make sure the sleeve hasn't moved axially, see that slight tube collapse where it bit in.
Okay. Beaded fittings, simple enough. Use the bead for a hose clamp.
Yep, low-medium pressure hose connections. Straightforward.
Now, flared fittings, the AN type. Sleeve and a nut, like in figure 918, needs that flared tube end.
Correct. The male fitting has a cone that matches the flare angle exactly. Creates a metal-to-metal seal. The sleeve is important too. Supports the flare, dampens vibration.
Which prevents fatigue.
Exactly. And a key warning, don't mix dissimilar metals. Causes corrosion.
They're color-coded too.
Often, yes. AN fittings. Black usually means steel, blue is aluminum, cadmium plate on aluminum bronze. Figure 919 shows various AN types. Figure 920 has useful data sizes, torques, bend radii.
And crucially, AN flared fittings are not interchangeable with MS flareless fittings.
Absolutely not. Different design, different seal. Figure 921 shows the visual difference clearly.
Okay, then MS flareless fittings. These are for the tough jobs. High pressure, high vibration.
That's their niche. 3,000 PSI systems, severe vibration areas. Figure 922 highlights that. 3 parts, body, sleeve, nut. Figure 923 shows them.
How do they seal without a flare?
The sleeve is the key. As you tighten the nut, the sleeve is designed to actually cut into the outside of the tube, creates a really strong mechanical grip and seal.
Clever.
And the body has a reverse angle inside to stop the tube collapsing inward when the sleeve bites.
We also saw some permanent fitting types. Swaged, Permaliter, Cryofit. Swaged are permanent, need special tools, often used with steel and titanium.
Yes, figure 924 and 925 show examples. Require hydraulic swaging tools. Only way to remove is cut the tube.
Permaliter.
Figure 926. Also permanent, attached by axial swaging using a specific permaswaging tool.
And Cryofit. Sounds cold.
It involves cold. Figure 927, often used in big transport planes for permanent hydraulic lines, especially titanium. The sleeve is made of tunnel, a shape memory alloy.
Shape memory.
Yeah. You freeze the fitting in liquid nitrogen, it shrinks slightly. Slide it onto the tube. As it warms up, it expands back to its original size, gripping the tube incredibly tightly. Permanent seal.
Wow. And removal.
Cutting only, like swaged fittings. Can't just swap in a flared fitting easily. These permanent types are all about maximum reliability in critical spots, even if they're harder to work with.
Makes sense. With all these different lines and fittings, identification is key. How's that done?
Markers. Color codes, words, symbols. Figure 916 gives an idea. They tell you the line's function, what fluid's inside, and any hazards.
How are they applied?
Often 1-inch tape or decals, like in Figure 917A. Or for tougher spots, like engine areas, steel tags, Figure 917B, or even paint.
And extra markings for function or hazard, like drain or flam.
Exactly. Drain, vent, pressure, return, and hazard warnings. Flam for fuel, toxic, PHDN for things like oxygen. Reinforces that whole oxygen hazard thing.
Who puts them on?
Manufacturer does it initially, but mechanics have to make sure they stay there and are correct on replacements. Put them near ends in each compartment next to accessories.
Got it. Let's quickly touch on general end fitting types. Pipe threads.
Common. Tapered male-female threads. Need sealant for a good joint, but never standard sealant on oxygen lines. Only special oxygen-compatible types.
Okay. Machine threads.
Straight threads, like nuts and bolts, used to pull connections together or attach to bulkheads. They need a flare or a washer or a seal to be leak tight. Sized by dash numbers like tubing OD in 16ths.
And bulkhead fittings just pass lines through walls securely.
Right. So the main connection types boil down to bead and clamp for low-medium hose, flared, flareless, and those permanent high-pressure ones.
So putting it all together, installation. Critical step.
Absolutely. First, inspect everything. Dents, scratches, right fittings, cleanliness, all before you start.
And no goop on the flare faces?
No sealing compound on flares or fitting faces. It messes up the metal-to-metal seal. Alignment is key too. Get it lined up before tightening. Don't force it with the nut. Figure 928 shows right and wrong ways.
Use the right torque.
Always. Especially for flared fittings. Figure 920 might have values. Too tight damages things, too loose leaks. Properly torqued flared fittings can usually be retightened a few times.
And flareless installation.
Hand tighten until it snugs up, then wrench tighten a specific amount like 16th turn for smaller aluminum, maybe up to 12 turn for steel or bigger tubes. Use a backup wrench.
Pressure test afterwards.
Always recommend it. If a flareless fitting leaks, maybe one small extra tweak like another 16th turn. But there's a limit, usually max 13 turn total past initial tightening.
If it still leaks.
Stop. Something's wrong. Inspect the tube, the sleeve, the fitting body for damage. Some makers give torque values for flareless too. Use those if you have them.
And over-tightening flareless is bad.
Very bad. Weakens the tube where the sleeve bites. Stick to that 13-turn limit. Common faults are things like distorted flares, cracked sleeves, rough surfaces, damaged threads.
What about inspecting installed lines? Can minor damage be fixed?
Sometimes. Shallow scratches on aluminum, if they're not in a bend, can sometimes be burnished out. Steel and titanium limits are usually much stricter. Always check the manual.
Severely damaged lines.
Replace them.
Yeah.
Always. Bad flare damage, replace it. Minor dents, less than 20% of diameter, not in a bend, may be fixable with a tool called a bullet, figure 929.
Or cut out a bad section and splice in a new one.
Yeah, using unions, like in figure 930. Swage fittings can also be used for some repairs. And always cap open lines if you leave them unattended. Keep dirt out.
And when replacing, make the new line match the old exactly.
Use the old one as a template, or make a wire template. And avoid long, straight runs. Bends are crucial stress relief. Thermal expansion, vibration absorption.
Gnar bends away from fittings.
Right. And the new line should fit without forcing it.
Okay, let's shift gears to flexible hose lines. Used where things move, vibrate, or need flexibility.
Exactly. Connect moving parts to stationary ones, absorb vibration. Connect metal tubes sometimes. Modern ones use synthetics, not just rubber.
Like Buna N, neoprene, Teflon.
Yeah, Buna N for petroleum fluids, butyl for Skydrol, EPDM. Critically important to match the hose material to the fluid. Wrong combo leads to failure.
Construction.
Inner tube, reinforcement layers, cotton or wire braid. Outer protective cover. Pressure rating depends on that braid. Low pressure, 250 psi, often fabric. Medium, up to maybe 1,500 or 3,000 psi. One wire braid. High, 3,000 plus psi. Multiple wire braids.
Stainless steel braid sometimes.
Yeah, for extra protection like on brake lines.
How are hoses identified?
Ley lines, those stripes running down the length plus markings. Type, manufacturer, date code. Figure 933 shows examples. The ley line also helps avoid twisting during install.
Specific markings like Skydrol use?
Yes. Always check the maintenance manual for the right hose type. Teflon hoses are interesting wide temp range, chemically inert, low friction, long life, often have stainless braid, good shelf life too.
Preformed Teflon hoses.
Used in tight spots.
Right.
But never try to straighten one. They suggest using a support wire inside if you remove one to keep its shape. Figure 934 shows that.
Inspection of flexible hoses, what to look for.
Leaks, obviously. Separation of layers, cracks, hardening, stiffness, or cold flow clamp impression showing the material has deformed.
If a swaged fitting on a hose fails.
Replace the whole assembly hose and fittings. If it has reusable fittings and they're okay, you might just replace the hose part.
Fabricating or replacing hoses.
Need the right hose, right fittings.
Yeah.
Check references like figure 935, 936. If we're using fittings, make sure they're serviceable. ID of hose must match the fitting nipple.
Assembly steps.
Cut the hose square, maybe slit the cover on high pressure types, screw on the socket and nipple carefully. Follow any lubrication advice. Disassembly is the reverse. Some hoses need braid sealant.
Testing after assembly.
Definitely. Proof test it. Liquid or gas, depending on use. Bleed air if using liquid. Gas tests often done underwater to spot bubbles. Follow manufacturer specs for pressure. Figure 937 might have examples.
Repaired hoses.
Recommended test is often 1.5 times system pressure. Use a proper test stand, like in figure 938, and always do an operational check after installation. Pressurize the system, check for leaks.
Hose size designation. Dash number matches tubing OD.
Usually, yes.
Okay.
Like figure 933 shows. Size, #8 hose for 12-inch OD tube connection.
Bending hoses, sharp bends are bad.
Very bad. Reduces burst pressure, can damage the hose. Use elbow fittings if needed. Or respect the minimum bend radius. Figure 940 has info on that.
Clearance is important too. Avoid rubbing.
Absolutely.
Yeah.
Check clearance through the full range of motion and install with some slack. 5 to 8% is typical. Accommodates pressure changes. Don't stretch hoses tight.
Support.
Yes. Support clamps every 24 inches or so is good practice. Prevents chafing, vibration. Retightening clamps depends on the type. Figure 941 gives general guidance. Non-self-sealing might need 14 turn if leaking. Self-sealing, maybe Singer tight plus 14 turn if loose.
Hose fittings swaged are permanent, detachable or reusable. Any others?
But you can attach hoses to beaded tube ends with clamps, as we said. Figure 939 shows reusable types.
Installation tips for hoses.
Maintain slack. Watch the lay line, no twisting. Use elbows for sharp turns. Allow enough bend radius. Support clamps shouldn't restrict flexing.
Hose clamps, torque wrench preferred.
Best way. Maybe 15 25-inch-pounds for small ones, but follow specs. Figure 941 has finger tight plus turns guidance if no torque wrench. Check tightness again after pressurizing.
Support clamps, rubber cushion for vibration.
Yep. Figure 942 shows those. Plain clamps for low vibration areas. Teflon, a cushion for skid roll or fuel areas. Bonded clamps for metal lines sometimes need to remove paint for bonding.
Use the right size clamp.
Always. And secure all lines at specified intervals. Figure 943 might show max distances for rigid tubes. So as you can see from the level of detail in the material you shared, what might initially appear to be, simple tubes and connectors, they're actually highly engineered components.
Yeah, definitely not simple.
They require a significant amount of precision in manufacture, installation, maintenance,
Yeah.
all crucial for aircraft safety and reliability.
Absolutely. We've really gone deep into the material science, the precise fabrication techniques, flaring, beading, bending, the multitude of fitting types, AN, MS, swaged, cryofit.
The critical importance of proper identification.
Right, the color codes, the markings, and then the installation details, inspection for both rigid and flexible lines.
It's a lot to keep straight.
It is. And you know what really stands out for me? That titanium and oxygen issue.
Yeah, that's a stark one.
A material praised for strength and lightness having such a critical vulnerability. It's a powerful reminder of the depth of knowledge and the vigilance needed in aviation.
Couldn't agree more.
This detailed understanding, like you said, really is a shortcut to being well-informed about a foundational part of aircraft tech.
It really is.
It makes you think, doesn't it? Just how much intricate detail goes into every single system on an aircraft. And, by extension, in so many other complex technologies we rely on where that same meticulous attention is just paramount for safety and performance.